check the 5-volt standby, right? On the plug here, going to the main board, and on this TV, on this board, there's a plug right here. It's going to the main board. If you get a dead TV, all right, with no standby light, no clicking, no nothing, and you have 5-volt standby, that lets you know it is the main board, most likely, right? All right, the main board, it could be something else, but it's not the power supply board. If you don't have standby, double check it, unplug the plug, whether you unplug it from this board or unplug it from the main board, unplug it, make sure nothing's loading it down, and recheck it. If you don't have 5-volt standby or whatever standby the TV uses, may use a 3.3 volt standby, like in a Sony, right? Or maybe a 5 volts or whatever, right? Or like in some Samsungs, it's 13 volts or 8 volts. If you unplug it and you don't have it, then you know you have a power supply board problem. Okay, you can replace the board or you can do some further troubleshooting. But today, what I'm going to do is do a common problem. Now, what commonly goes wrong on a dead set that is being produced by a faulty power supply board is, take a look at the schematic here. It's a drawing, all right, of a switch mode power supply. Okay, now I did a video on this schematic and how power supply boards work, especially in the TV. If you haven't seen that video, make sure you check it out, because if you look at that video, this is what I'm going to say in this video is going to make it sound much easier. It's going to be much easier for you to follow along. Okay, so quick rundown. We got AC in right here, right? We got our AC in, right? We got the main fuse, okay? All right, then it goes through what they call an EMI filter, or electromagnetic induction filter, right? That's going to smooth out the AC. We have a safety device here, okay? All right, so same thing here. AC in, fuse, get our filters, okay? Right? A little inductor, capacitor. Capacitor, inductor. And most power supply boards, they're all the same way, okay? And then we have another safety device. This could be a fuse or a NTC, which we have right here, over voltage control, which is the green also right there. Then we have our rectifier circuit, which changes the AC into DC, right? And using a rectifier diode, full wave rectifier, which we can see right here, okay? Right, all right. And then after that, we'll go through our power factor correction circuit, okay, which uses a inductor or a transformer and some diodes. And as we see on this one right here is our power factor correction transformer. It's really an inductor, but it's like a transformer. And then we have some more diodes right here. All right, now that normally turns on when the TV is on, okay, to boost up the 300 volts or whatever on here. It's going to boost it up some more. All right, and then we get through. We're going to have our main filter capacitor, which is located right here. Okay, it's always a big one, right there, main filter capacitor, and then we have our switching transformer. Okay, right here. All right. So the main things that are under the most stress are going to be the FET that switches the transformer on and off, all right, and also a FET or anything that's going to be in your power factor correction circuit. Most likely between these two, most likely this one for the main transformer is going to be one that's going to be shorted or faulty and giving you a symptom of a dead TV set. Okay? All right, so let's just start with this board first. This board here is a, if you look on the sticker here, all right, this board is a this board is a BN44-00667A. It's out of a 40-inch Samsung LED lit TV. Use the LED strips, traditional LED strips. There's the plug for the LEDs here, right? See the LED circuit here, and this obviously is the plug that's going to our main board, okay? So, okay, and I did have someone ask me about where do I find the part number on these Samsung power supply boards. this is how you do it. You want to go with the number off the sticker. Okay, maybe you're printing on the board, but this is the exact number for this board. What you do is you start off where it says BN44. All right, so you're gonna have be a BN44-00667A. Right? The plug going to the main board. We're gonna check for the standby voltage. Okay, now this one uses 13 volts standby, I believe. All right, as you can see, it says 13 volts. We have a backlight on, command, 13 volts, B5 volts, B13 volts. All right, and it's also marked some test points on the board. There's one here that says 5 volts, and the one right here says 13 volts. All right, so let's check that. Here, yeah, this is hot here, and the cold side is here. All right, so this is obviously the cold side of the power supply. So I'm gonna run my meter right here. Okay, that should be cold ground. Okay. So I'm going to plug in my AC. All right, I'm being very careful when I do this. I am using an isolation transformer. Okay, very, very careful not to touch anything on the board with your hands, especially on the hot side, especially this filter capacitor right here. Okay, all right, so we're gonna go check, instead of having any voltage on here. That is looks like the 5 volts. There's nothing there, and there's nothing there, okay? No voltage. Now, if you're unsure, all right, let's say if the board is not marked, you can always just check each pin on this plug that's going to the main board, okay? If you don't come up with 5 volts, 13 volts, or the 3.3 volts, you know, on none of the pins, to let you know that you're not getting standby, okay? We need the standby when the TV is plugged in. Even though the TV is not powered on, when the TV is plugged in, we need the standby voltage going to the main board. That way, when you hit the button on the remote or remote control or on the actual TV, the TV is ready to turn on. That's what they call it, standby. It is standing by waiting. The voltage is standing by waiting for you to do something, turn the TV on, right? Okay, so we don't have anything here. All right, so I'm gonna unplug it, okay? Now, it's like I was saying, on the schematic right here, or we all want to check what's you doing the most work, and that's for the switching transform. That is the switching transformer, right? Okay, and the FET that's switching the transformer. All right, now that's where it gets its name from, because the transformer switches on and off so fast, 10,000 times per second, 100,000 times per second, whatever the frequency is, that it actually induces voltage onto the secondary side of the winding. It creates energy by it cutting on and off so fast, right? Via this FET, via the FET driver, right? It's going to the gate. All right. I'll give you a prime example. Those hangers. Remember the hangers your mom used to whoop you with back in the day, or grandmama, if you're an old guy like me, right? The actual metal part, take the cardboard off, and the metal part, remember how you used to bend them real fast and break it just so you can break it off? You bend those hangers, and when you're bending that, if you actually touch it, right, it's real hot there, okay? Because you're creating energy and heat by you keep doing all this until it breaks off, right? So it gets very hot, and that's how it breaks off, all right? Same concept, right? Okay, so this is the main transformer because one side is in the neutral, one side is on the cold side. On the cold side, the other side is on the hot side. As you can see, there's a line right here going through there. All right, so we're gonna find our transistor, most likely, it's right here, okay? These three right here, all right? So obviously these two, or one or whatever, is for the PFC circuits, the PFC transformer. How do we know that? Because the PFC transformer or inductor, right, is always, it's not isolated, it's always in the hot side, all the pins, right? And as you can see, that is in the hot side, so the whole transformer. This transformer here, as you can see where the line is, right? Pins, it's isolated, okay? So we get pins going here on the secondary side and the other pins on the hot side. It even says hot right here. All right, so obviously we're gonna check those first, okay? So I'm going to put my meter in diode. All right, so let's see. And I got the three here. I'm gonna check all these These FETs, I'm assuming, right? Okay. It's good. Okay, where's my next one? Right here, looks like. Let me get my other glasses, I can't see. Hold on. Okay, this is actually a diode. Alright, so it's a diode for the power factor correction circuit, obviously. Okay, so that's good. And then this last one here, that, my friend, is shorted. Okay? That is a dead short. Let's do it like this. Hit auto. Yes. That is dead shorted. Alright? Okay. Now, obviously that's a short, and with the plugging in, it must have blew the fuse, right? So let's go check our, see we got one fuse on here, our main fuse, right here. Let's check that, it should be beat, it should beat. Right? That fuse is open. Okay? So that could be our problem, right? So we'll just go ahead and replace that. The numbers on here looks like a 60R360N. Alright, so it's like maybe 600 volts. Yeah, 600 volts, maybe 6 amps. I don't know, my camera's gonna pick that up. Probably not. Nah, it's not gonna pick that up. But I'm going to replace that and the fuse, and we'll see what we get. Okay, so we replaced our fuse. Okay, so I just used like a pico fuse. I know there's some fuse police saying, "Oh, that's not the right one. You should put the right one in there." Hey, I don't give a dang. So you know, it's just 4 amp fuse. All right, and so that's good. And we replaced our FET. Okay, right here. So this is the one that actually drives the switching transformer. Okay. So what I'm gonna do now is I'm gonna go ahead and check and see if we have our standby voltage, which should be on right here on these pins. As you can see, it actually does say 13 volts, at 5 volts here, which just says 5 volts, and it should be 13 volts. So one of these should be active as soon as we plug it in, okay? I'm gonna plug her in. Okay, no smoke. Nothing, okay? Board's plugged in, double checking that. All right. Nothing. 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 And what I'm gonna do is to make sure I'm gonna check all these pins. Be very careful when I'm doing this because it's still plugged in. I'm gonna go to the actual plug and double check it. Nothing. Nothing. I just want to make sure that I'm not getting anything on this plug at all. Right? So that kind of sucks. Alright? Nothing. Well, the first thing, am I replacing that FET, that shorted FET, and it's still not getting any voltage on the secondary side or standby, is I'm going to check the fuse again, make sure the fuse didn't blow. Okay? So I'm just unplug it from right here, get that out of the way. And so here's our fuse here. Whoops, I always skip that, right? We'll just leave it auto, or I can put it on continuity. It's a little faster. Beep. All right, so let's see. Fuse is still good. Let me check this FET again. All right, this FET right here. Obviously, make sure that's not that didn't short back out. Let's put it in diode. It's kind of weird. Okay, no, the FET's not shorted. At all. No sorry, Bob. 1.8 volts that way. Yep, 0.5 volts. So that FET is working. So let me see here. So what I'm gonna do now is I'm actually gonna see if I got any B+ or DC voltage on the primary side, right? So we should have maybe like 100 and I don't know, 60 volts on that FET. If we do have the voltage there, but it's still not switching the transformer in order for us to get voltage on the secondary side, that means that we may have a drive problem. So, replace the FET and the fuse. Still not getting standby voltage. Fuse is good. FET's still good. Now I want to see if we get any voltage to come up. All right. Okay, the capacitor is right here. That's negative. That's positive. So negative is going to ground, hot ground, right? We're on the hot side. And one of these, the source pin, which should be right here, I believe. Here we go. That is going to ground. So the gate pin was being driven by this IC. This is the Pulse Width Modulator IC, PWM, right? Okay. And the drain is what's connected to the primary winding of the transformer, okay? So we should be getting voltage here or either on the capacitor. So let's see. And our FET is up here. Let's turn it this way. Okay, so now our FETs, is our FET. We changed right here. Okay, this is our capacitor. Want to make sure that we see if we got any DC voltage there, right? So, well, first we check across the capacitor. Make sure I'm in DC volts, right? Get 164 volts. DC. All right. So I'm going to keep my lead on the negative side of the capacitor. I'm going to go to the FET. I'm going to go to the drain pin. We should have 160 volts here. We do. Ha ha. So 160 volts there. And that's it. Now, what I want to do is, I think the problem is, since we're getting 160 volts right there at the FET is going to the transformer. The drain should be going to the primary winding of the transformer. So let's see where we're at here. Yeah, right here, right? One of these pins should be reading 160 volts. Here we go, right here, okay? There we go. Okay. 164 volts, but we're not getting any secondary voltage. We're not getting standby anyway. All right, so what I'm going to do next is I'm going to see if we're getting any drive at the gate of that FET. So I want to go here to the gate and see if we have any kind of, see if I can read any type of frequency there. Now I'm assuming that this FET is switching at approximately, or the gate, right, is switching at approximately 100 megahertz, 50 to 100 megahertz, right? So let's see how we get frequency on here. We just go here, 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 here. So we're getting 60 hertz there. Okay, obviously we're not getting anything. Nothing. Okay, so that's what we're going to do now. Is we're going to check the driver chip, the Pulse Width Modulator for that FET. All right, so where are we? That is going to be right there. See how close I can zoom in on that. That I see right there. Okay. It's a SOP7, which means it has 7 pins instead of 8. There's 1 pin missing. It's not connected. So that is our Pulse Width Modulator IC. And I want to check that. I think the part number was SSC3S111. Okay, this was on the chip. And I can't, of course, if I zoom in too close, it's going to start getting blurry. So let me see. Yeah, it's a 3S111. Well, let me zoom out. And so the first thing I want to do is, I obviously know that this is the FET that drives this transistor, all right? So just like, or drives, this is, I'm sorry, I know this is the IC that drives that Mosfet, right? So, just go over this one more time, just so you know what's going on here, all right? This is the driver IC that drives the gate of this FET to turn that 160, what was it, 164 volts? The 164 volts that we have here, it needs to be turned on and off. And let's just say we're at 50 kilohertz frequency. So it's doing the full cycle, on, off, on, off. Okay, that's the signal, but the one cycle is on, off. All right, until the next cycle begins. So it's going to be doing that approximately 50,000 times a second, right? And we need that in order to energize. So what's going to happen is, if you're cutting this transformer on and off at 162 volts, on, 162 volts, off to 0, on, off, 100,000 times or 50,000 times per second, quite naturally, you are going to produce energy in the secondary winding, right? Like I was explaining earlier. Okay, so we need that voltage, otherwise it's just sitting there, right? Okay, it's not doing any work. What I want to do is make sure that we are in good standings on that driver IC, or the PWM, Pulse Width Modulator, right? So what I'm going to do is pull out a data sheet on it, right? Because I'm going to start checking the pins on it. Okay, so here is a very good explanation of what's going on here, all right? This is the same IC. Well, it's not the exact same one, but it is the same one. All right, so it's the same, pretty much the same one, might have a different current rating or something like that. That's why the numbers are a little different, but other than that, the pin outs are the same, okay? So this is our drive pin. Okay, that is what is driving the gate of the Mosfet, correct? That will be pin number 5, okay? So we should be getting some type of drive there, okay? We definitely need VCC. That's usually between 7 and 12 volts, I believe, depending on the circuit, to make the IC start working or switching correctly, right? Okay, and then what else do we need here? We need a startup voltage, okay? Because what happens is this IC is not going to get VCC, working VCC, until it gets the startup voltage. All right. So until it starts the transformer right here, which you see right here, until it starts that up. Once that starts up, it produces voltage not only in the secondary winding, but also in the auxiliary winding on the primary side still, on the hot side, and that's what's going to give you your VCC. I believe that's usually how it should work. Let's see. Yeah, VCC right here. Okay, so there's also on this winding right here. So, so the IC has to start, of course. The IC has to start switching, so we can so the transformer in effect can start switching. So that's what the startup voltage is for. All right, which says ST. We need that, and that is coming directly from the DC voltage source between the rectifier diode and the big filter capacitor. The only thing it's doing is being stepped down by some high value resistors. All right, most cases. So anyway, enough class on how that works. So we're mainly concerned and make sure that none of those pins are shorted, right? Especially VCC to ground and ST to ground, right? And if you're getting a short between OCP and ground, then we don't have a problem there. But what I'm going to do first is I'm going to check and see how many voltage going there, right? Circle. That's pin 1. So it's pin 1. I can keep still, okay? 1, 2, 3, no connection. 4. Jump to the other side, that's 5. So it doesn't go like this. 1, 2, 3, 4, and then 5 at the top, 6. No, it goes 1, 2, 3, 4, 5. It's straight across from 4. 6, 7, 8. So pins 1 and 8 are at the top of the IC, and pins 4 and 5 are at the bottom of the IC. All right, and notation here, this circle is all letting you know that that is pin 1. All right. Okay. So once again, our main concern is the VCC that we should be getting. Okay. All right, and quite naturally the startup voltage. Okay, which is going to start this process So as soon as it gets a startup voltage, it should start switching. And once it starts switching, like I said, we want to expect the VCC to come in right after that. Okay, it probably won't be noticeable with the human eye on the meter, but that's how fast it works. All right, so we're concerned with the VCC pin. 8 is ground. Okay, there's a pin on top, VCC pin, and startup pin. We'll make sure those are not shorted to ground, and see if we have any voltage on pin 7 and pin 4. Sorry, that's the wrong IC. We're right here, okay? Now the other IC obviously is for what? To switch the MOSFETs on and off for the power factor correction circuit, right? Those little transformers, little inductors, or big inductors, whatever you want to call them, has to be switched on and off also to upgrade, or how you want to say, upgrade or to increase the voltage, right? All right, once the TV set is on, right? So this here, my meter is in DC volts. I'm grounded to the capacitor right there, okay? That's hot ground, because we are on hot ground now, okay? The transformer is being driven, everything is on hot ground. Just remember that, all right? And then we have pin 4, which is our startup voltage, okay? And look at that. We have startup, 7.5 volts. Good thing, right? Lets us know that most likely our DC rectifier circuit is working. All right, so pin 6 is overcurrent protection, nothing there. Pin 7, which is VCC. Now we should be getting that. It's pin 7. Nada. We have nothing. Move this over a little bit. We have nothing. We're not getting the VCC. So that lets us know that there's no switching going on. There's no party going on, right? So think of the transformer. So think of the transformer, right? This is the primary, let me mark this. This is the primary windings right here, okay? Okay? And so this obviously, as you can see, this is the drain from the FET that was shorted, we just changed. It is going right to the winding in the transformer, right? Just like on this one. Drain, going right to the winding on the primary side of the main, the switching transformer. The main, this is the auxiliary winding. This is the main winding that kickstarts everything. So think of it like this. This is the club, right? This is the club. Okay, this transformer is the club. You got 168 volts. So you got 168 people standing outside waiting to get in, right? They're on the hot side. When you're outside, you're on the hot side. It might be hot outside, or it might be some shooting going on, right? So, so you're trying to get inside into the club, and the only way you can get in is if the door's open, the gate's open. They're gonna open and close, right? Open and close, open and close. Come in, come in, come in, come in. Wait line, come in, come in, come in, come in. One by one, right? So, in order for those 160 people to get in, or for the 160 volts to get in and get into the club on that side, on the cold side where you're safe, we have to start switching the doors on and off, right? And what I'm gonna do now, I'm gonna put my meter in. Let's just go to. I want to go to dial. We can't go to dial, but I want to hear any beeps in case something is shorted. Let's go to continuity. All right. Okay, that's continuity. And let's start. Pin number 8 is ground. So this is obviously pin number 8. Ground. Good. All right. So let's make sure that pin 7, VCC, is not short at the ground. Let's see. Make sure we should have a high ohm reading. 44 ohms. That is way too low. All All right. Let's go to pin 6, overcurrent protection. $69 ohms, not quite. Okay, pin 5 is the drive circuit. That looks good. Okay. Now if that was short to ground, we'll probably blow the actual FET out again. All right, so, all right, but this here, pin 7, VCC. Let's look at it again. Pin 7 is the VCC. The actual VCC for the IC, so it can start working and keep working. Should not be 44 ohms. Let's go to diode scale. Yeah, that is way too low. That's ground. .0, that is too low. I'm so sorry, too low. Now, another thing I want to point out is the VCC always has a capacitor that's supplying it. And of course, it's not going to short on this diagram here, or is it? Let's see, VCC. Yes, right here. Okay. So obviously, the VCC pin right here is going to have, in most all cases, 47 microfarad capacitor. Okay, so that's how you know that is our power supply for our VCC. We have another capacitor going on the ground, and of course this is our diode, right? And of course that is definitely coming. All right, so I can't. I'm sorry, you couldn't even see that. All right, so here we go. Capacitor right here. 47 microfarads at 50 volts. So let's look if we can find the capacitor. And I actually can trace that. Let me see something. Let me see if I can trace that capacitor. All right. Let me just see here. VCC pin, pin 7. Okay. Should be going to a diode, and it goes to these two. Let me see here. Okay, it's going this way also. So goes this way, and here's a capacitor right here. Okay. If I go across from negative to positive, I'm getting the same reading, 46 ohms. Now we know that's wrong because there's no way in the world a capacitor, an electrolytic capacitor, should be reading 46 ohms from the positive to the negative side. Okay, that's almost a dead short. All right, so I did check the capacitor. Let me see if I can check it here. Put on capacitance. It says 47 microfarads. I'm almost guaranteed, while you're looking at it, it's at 47 microfarads. That is the capacitor that's going to, once again, that is the capacitor that's going from here to pin 7. All right, and let's see what I got. Hold it there. So I don't know, it's still in the circuit, so there may be an issue. But my main concern is that I'm pretty sure that it is the IC. So I think what I'm gonna do, I can't pull the capacitor out, but I think I'm gonna pull that IC out because, number one, the Mosfet shorted out, right? So, and this connects directly to the Mosfet, and we're not getting any drive. Is there anything else that could be shorted here? Let me see. I'm gonna double check. like a diode. Good. You don't have to make a physical inspection. I don't see anything that looks burnt, especially these resistors, right? Okay, that is a coil there. Okay. All right, so that should be reading short. Capacitor looks good. Capacitor here looks good. These are all good. Okay. Wait a minute. That's 44. Okay. So that's coming from my VCC. And where's this going? Oh yeah, to our negative side. Okay. Right. Yeah, so that's the negative side. So pretty much, look here again, VCC. It's going up. Electrolytic capacitor, 47 microfarad capacitor, and then some diodes that are going to ground. I'm sorry, some capacitors that are going to ground. Okay. If I look, I can actually see that those numbers on, that's the number of the IC, 3S111. So it's pulse width modulated with current control. All right, so okay, good clean swipe. Let me check and see if the short is still there. We'll just go across the capacitor right here. Let's see. The capacitor is the one that was reading short also. 100 ohms. All right. Was at 44, now it's at 100. And still maybe kind of low. Let me see here. And pin 8 was ground, obviously, right? Let's see, ground. Okay, pin 7, here we go. Looks like we're good, okay? Let's check this capacitor. Let's see. Let's just make sure. Let's take one end out because that 100 ohms seems a little bit low to me. Once again, 47 microfarads, right? 47 mics, 50 volts. So I'm gonna do first is see resistance across the resistance across there again, and what the capacitor was. This is the capacitor for the B plus. Wow, bro. Now we're at 770K. Okay, now that's where it should be. Now let me go over here to ground. All right. Let me go to ground. Okay, let me go to ground here on my IC, or even we'll go to negative side to put the capacitor right here. And let me, this is ground. Okay, yeah, that's ground. Pin 8. Pin 7. $180 mega ohms. Okay, now this capacitor, let me just see here. That's kind of weird. This capacitor is reading, hold on a second. Okay. All right, so actually what I'm gonna do, I'm just gonna check the resistance on this IC between ground, which is pin 8, and VCC. All right. So this diagram is pointed up just like the actual IC is pin 1. All right. And I forgot, but just make sure that you mark pin 1 on the board before you pull any type of IC off of a circuit board. Okay. So pin 8 is ground, so let's go between pin 8 and pin 7. All right, and let's see what we get. Hold steady. Yep. So, remember before we're in the circuit, we're reading 44 ohms. Okay, now let me check this capacitor. Okay, and let's see what kind of reading that we get now. It says 48 microfarads. Let me do a resistance check. Hold on, let me see here. Now I wonder why we're at 12 mega ohms. All right, it says mega, can't see the little M down here on my meter. It's at 12 mega ohms. So I wonder why this is reading in the circuit. It was, after we pulled the IC out, it was only reading 100 ohms, but as we took it out, it's much higher now. Got full crispy, brand new. On this new one, let's go between pins 7 and 8 and see what kind of ohms we get. Yep, 2 mega ohms. Just gonna keep still. You seeing that, right? 2 mega ohms one way, and the other way is infinite. This should be all it needs. It needs. Double check before I start soldering. Make sure I get the polarities right. Because if you get those polarities wrong, you are probably going to see a little smoke. Meter in DC volts. I'm going to go ahead and check standby. All right, DC volts. The first thing I'm going to check, once again, ground my meter on. This is our plug, and these are our voltages right here. All right, so I'm going to check those jumpers or test points first. Okay, grab my meter and plug in my device. I hear something. I hear something. Let's see. There it goes. 12 volts. 12 volts. And 5 volts. That's it, guys. We're done. Okay, guys, let me see if I can get a frequency reading. Okay, before we pull our scope out. Okay, I hear the power supply board running. All right, and let me go to the gate of this Mosfet, which is right here. Okay, it's switching around for some reason. Maybe I don't know why. Could be this meter too. I got it in frequency, so it says kilohertz. But I'm gonna hold it on the gate. Remember before when we were holding on there, it was saying 0. Now it's saying approximately 46 or 45 kilohertz. So let me go ahead and plug it in, and let's check some of these voltages on the IC. Okay, I hear it whining. And first thing I'm going to go to is the VCC voltage, which should be 1, 2, 3, 4, pin 8. I'm sorry, pin 7. All right. We are at 15 volts. Okay, so we got our VCC voltage, and let's go to pin 4, which is our startup voltage, which is 7 volts before. Let's see what it is now. Holy shit, 380. Oh, you know why? I forgot. This TV is the one where you unplug it, plug the main board, and the backlights light up, letting you know the power supply is good. So the TV is actually on now. So which means the power effective compression circuit should be on. So we should be getting that across the capacitor now, instead of the 300 and instead of the 160. Well, 162 we were getting before. Let's see here. We're getting 380. There it is. 380 volts, 86 volts. And by the time it gets to here, so our startup voltage, pin 4, it is actually 382. And if we follow this, pin 4, the startup pin, is going through a series of resistors right here. Okay, it looks like 3202, 33K. Yeah, 33K. All right, so that's 3 of them. It's 386 before it gets to the resistors, and after it gets to resistors, the last resistor is sitting 382 to the startup pin on the PWM chip, right? And it's our capacitor right here, our main filter capacitor right here. I'm sorry you couldn't see that. Capacitor, resistors, 3 resistors, and that is going straight to the startup pin. So once that pin starts up, it's going to once that pin gets to 382 volts, it's going to start switching. All right, and after it starts switching, it's going to then provide the VCC voltage, which is 15 volts, and it is steady. Okay, so now let's check our drive signal. Okay, I'm going to go to the gate of the Mosfet, about 43 megahertz right there. Hopefully you can see that. Okay, and I'm going to go to the gate of the FET. Should be a little clearer, a little faster, and Looks like we're running at probably about a 10% duty cycle. Looks like that's at 70 kilohertz. And let's go to the actual drain, which is going to the transformer. Matter of fact, we should be getting the same reading right at the transformer on the primary side to one of the pins here that is going straight to the drain of the Mosfet. And there we have it. That's how our transformer is switching right now. Alright. Looks like it's almost at, for some reason I can't find how to get the duty cycle on here. Single. Okay, so obviously from here to here is one cycle. Alright, it looks like it's on probably about, we don't have a load, the main board hooked up to it, so evidently when we do, it's probably going to be a little bit fuller, right? So that looks good, guys. Looks like we are in good shape. Okay, guys, we're done. Make sure that you do subscribe. Please like the video. And until then, I will see you guys in the next one. Big Dog out. That's it, bro. We're done.